this is just a representation. The thing is, everything's so different in this world of atoms and molecules, it's not really possible to appreciate these things with just our normal everyday perception of things. So don't pay too much attention to the precise details, but it's just a way of looking at it. So in the centre there's a nucleus made up of neutrons and protons. Neutrons don't have any electric charge, and the protons have a positive charge. And then around that there are shells of smaller lighter particles, electrons, which have a negative charge, and the negative charge bounces out the positive charge of the protons. First of all, I'm just going to give you a simplified model of the mass of an atom, which is the way it was first introduced to me when I was at school, and historically this was the way it was viewed. Later on we will look at the full analysis of the mass, but this gives a simpler understanding which is perfectly adequate to understand how this mass spectrometer works, although there are some fascinating things to do with the full understanding of it. So really the simple view of this is just that protons and neutrons are the particles that give an atom its mass, and a proton weighs the same as a neutron, and electrons have negligible mass. So really, like this, the mass of an atom just depends on the number of these things in the middle. It's an integer that depends on the number of these, and actually it's these things around the outside, the electrons, that determine the chemical properties apart from the mass, the weight. The mass of course depends on this, but the way atoms and molecules interact with other atoms and molecules is dependent on these electrons, because those are the things that connect and join them to other atoms and molecules. Well, if we have a look at the periodic table, this is a dynamic periodic table. This one was made by Michael Dyer. There are some other ones you'll find on the net, but these are fascinating things. It sort of brings the periodic table to light a bit. You can move the cursor around and select any one of the elements, and you see over on the left it's telling you its name, and below all sorts of details of that element. And then you can see also that with the colours you can see from the periodic table which elements are metals, which are non-metals, and other characteristics of them. You can also see which ones are solids, liquids and gases, and there is a temperature you can set here, and as you change the temperature you can see how all the elements change from liquids to gases and solids. Also an important thing to understand about the periodic table is why it's organised as it is. You see there are these gaps in the middle, and the reason it's laid out like this is so that certain elements are above other ones. I mentioned these shells that are full of electrons. Well, the shells are governed by very strict laws in our universe as to how many electrons can be in those shells, and there is a sort of a precise number that can be stable, or maximum number anyway. When the shell has got a full number of electrons, it's quite stable, and all these elements down here on the right hand side have got full shells of electrons, and these rows represent the shells as they fill up. So along the top here, this is the first shell we saw in the diagram I just showed you. So the element with 1 electron is this one here, the element with 2 electrons is this one here, and that's got a full shell, and then the one with 3 electrons will go back over here, and we'll carry on along this row here until we fill that shell up, and then the one with 1 more will come back down here. And the reason they're arranged like this is because elements have characteristics that are dependent on how full the shells are. So all the ones down here that have only got one electron tend to be unstable, and the ones here that got full shell tend to be stable. And then you can see a block here of elements, and the reason they've been put down the bottom here and not put in here is because if they were put in here, then of course it would make the table so wide it wouldn't fit on a page. Well, the element we saw that had got 4 things with mass, 4 neutrons and protons in the middle, will have an atomic mass of 4 units. And if you look on the periodic table, along the top here there is a thing called the atomic number, that's the number of protons, and if you look along the bottom here there's the atomic mass, that's the total number of protons and neutrons. And so you can see from this which element that was that we had the drawing of. If you look at a mass spectrum of that element, that is what a mass spectrometer is all about, showing the mass of these things. I'll show you that. So this is the molecule, it's got an atomic weight of 4, and if you looked at its mass on a mass spectrometer it would look like this. The mass spectrometer shows you a horizontal line which is calibrated in mass, so this is numbers along here, and at this point here we've got 4, and on the vertical axis it shows you the abundance of things of this particular weight. So it's not just like weighing a fruitcake and saying how heavy the fruitcake is, it's telling you how much abundance there is of all the various things in this mixture that have got a specific weight. So if we got something with a different weight, that would appear as a different line here. Now, looking back at the periodic table, on this simple way we're looking at things, that things have integer weights. Well, historically, when the periodic table was first being put together, it seemed to fit with what was thought to be the theory that the elements discovered seemed to have integer weights. And then one was discovered chlorine here, and chlorine's got a weight of 35.45 here, and that caused a lot of confusion because this didn't seem to make sense. It didn't have an integer weight, and how could it be that it didn't have an integer number of protons and neutrons? Well, if in those days people had mass spectrometers, they would have understood more easily what was going on. It was worked out in the end, and if I show you a mass spectrum of chlorine, that's like this. This is the mass spectrum of chlorine. So there are 2 types of chlorine. One type of chlorine has got a mass of 35, and the other has got a mass of 37. So if you have something like a mass spectrometer that can distinguish between these 2 different types, or isotopes as they're called, you can see that there are 2 different types. But if you were doing an experiment that involved determining what the density of a known number of or the weight of a known number of atoms or something like this was, you would be a bit confused, because these ones are more abundant than these ones. You tend to end up with an average weight of about 35.5, somewhere about here. So the figure you see in the periodic table is 35.5, I think 35.45. So an important thing here to understand is that the masses given in the periodic table are different to the exact masses that you would measure with a mass spectrometer. The masses in the periodic table are the average of the normally occurring isotopes. Now, another thing to consider is if we can only measure integer masses with a mass spectrometer, that's probably fine for looking at elements in the periodic table because they all tend to have different masses. But, well, there are only so many integer masses, of course, and since there are absolutely billions and trillions of different compounds that can be made from the elements in the periodic table, there simply aren't enough integer numbers of atomic mass units to go round. So you might think, well, a mass spectrometer isn't going to be able to identify all these different compounds. Well, there are other ways that a mass spectrometer can do this. Let me show you another plot. This is the mass spectrum of water. Well, water, H2O, consists of one oxygen atom and two hydrogen atoms. An oxygen atom is 16 atomic mass units and hydrogen is 1 atomic mass unit, so water is 18. So in the spectrum of water here we see one line at 18. That is the mass of a molecule of water, but also we see these others. And what happens is when you look at a molecule in a mass spectrometer, as well as showing you the mass of the molecule, it also tends to fragment the molecule and breaks it up a bit. And it breaks it up in a predictable way that gives you a sort of fingerprint of that molecule. So this is the fingerprint of water. Now it's important to understand the distinction between this and the mass spectrum of chlorine. This is a fingerprint of water that's been caused by the mass spectrometer breaking up the molecule in a predictable way. In the case of chlorine, this is something different. It's not something that's been broken up. These are two different isotopes of chlorine that naturally occur. Well, there is another way that a mass spectrometer enables you to identify substances that have the same mass. So just to reiterate, I'm saying with water that this is the mass, this is the molecular line of water, and with water it's got this fingerprint. With something else that had the same molecular weight as water of 18, it's likely that it would break up in a different way and give a different fingerprint. But another way that a mass spectrometer can look at this, now the sort of mass spectrometer that I've built, a quadrupole mass spectrometer, which isn't working quite right at the moment. At the moment the resolution isn't quite as good as this. You will see when you see it working difficulty in distinguishing these peaks of water and oxygen. But with a high resolution mass spectrometer, which are normal commercial things that are used for certain purposes, it's possible to get very high resolution and look down in great detail at exactly what the mass of these lines is. Well, this is known as the nominal mass, just the integer number, the number of neutrons and protons. But if you look very precisely, you'll see that there is a precise number that is not an integer. Now it's important to understand that this is different to the number that you see in a periodic table. In the periodic table, the number you see, the number which has got decimal places, that is not the exact mass, that is the average mass of the isotopes, as I explained with chlorine. But if you were to look at just one of these lines, such as one of the lines of chlorine, or this line of water, it's possible to measure its mass precisely, and you'll find that it's not an exact integer. And the reason this happens is if you look at all the elements in the periodic table, they all have protons and neutrons, and also electrons, which contribute to the mass. The mass of a proton is not exactly the same as the mass of a neutron, it's very close, and the mass of an electron is very small, but it does have some effect. But there is an additional effect which can be measured, and that is that there is energy which holds these protons and neutrons in the nucleus together. In chemical reactions and in mass spectrometers, we fiddle about with the electrons, but under normal circumstances nothing disturbs the nucleus. There's a lot of energy that holds all this together. Now this energy has to be accounted for, and so the fact that there is this energy stored up in the nucleus causes the mass to be different from just the mass of the protons and the neutrons. And this tends to be different for different elements of the periodic table, because the arrangement of protons and neutrons is a bit different, and so the energy is different. So this means that there is you can make a precise measurement of the mass of an atom, and this will give you another indication of exactly what it is. This doesn't matter so much for looking at elements, of course, because we could identify those just by the integer number of protons and neutrons. Two molecules that have got the same number of protons and neutrons in them, and so simplistically you might expect them to weigh the same, but because of this mass defect, as it's called, it's possible to distinguish between them. So this I think is a fascinating thing. This shows Einstein's law E equals mc squared at work, showing that the mass of things is not what you would expect it to be by their component parts. It's changed slightly because of the energy that's stored up in them. That's explained a little bit about chemistry. I'll just explain briefly that the way mass spectrometers work is simply by applying Newton's laws to the movement of atoms and molecules. You can see from what we've said that the internal workings of atoms is very much tied up with things way beyond Newton's laws, with quantum mechanics and all sorts of things that are difficult to understand. But the way atoms and molecules behave when they are accelerated by forces can be explained quite adequately by Newton's laws, and really this is all mass spectrometers do. First of all, the way a force is applied to an atom or molecule is one of these electrons is removed. So the atom or molecule is subject to a stream of electrons which approach the thing we're trying to analyze, and because these shells only allow carefully controlled configurations of electrons, when another electron occurs and there's one too many, this causes the thing to become unstable and it gets rather wobbly and electrons fly everywhere. And once an atom or molecule has lost an electron, because it's in a vacuum in a mass spectrometer, it's not possible for it to regain an electron. So once it's lost an electron, it's then unbalanced and it's positively charged, and so then the atom or molecule can be accelerated in an electric field, and then when it's moving due to this acceleration, then it can have other forces applied to it, and the way it moves will show how heavy it is. In a traditional mass spectrometer, this is done with a magnetic field, and this is the simplest type of mass spectrometer to understand. The one I've made is not a one using magnetic deflection. This one is what's known as a quadrupole mass spectrometer. These are the most common ones in industry. A quadrupole mass spectrometer doesn't need quite such a high vacuum. That's one of the reasons I've used this technique. A quadrupole mass spectrometer can't give a very high resolution mass spectrum. That has to be done with a magnetic separating mass spectrometer. Have something known as double focusing to get a precise measurement of the mass. Well, I hope that's made a bit of sense about the very basics of chemistry and how mass spectrometers work. Thank you for listening.